Welcome back to the deep dive. Today, we have a mission. It's a mission that I think everyone listening will understand on a deep, almost painful level.
Oh, yeah.
We are going to tackle that moment of pure physical misery when your own winter clothes betray you.
We have a pretty dense stack of sources today. We're diving into some serious material science, specifically the work of Shuqiang Li and a whole team from Nanjing University of Aeronautics and Astronautics.
Right.
They're engineering something they call sweat-sensitive adaptive warm clothing, SAWC for short.
But just calling it warm clothing really doesn't do it justice. It misses the whole point.
Not at all. This is clothing that, well, it listens. It pays attention to what your body is doing.
Okay, so let me set the scene, because everyone, and I mean everyone, knows this feeling. You're stepping outside. It's brutally cold. Maybe it's 5 degrees, maybe it's colder. You could be starting a long shift working outdoors, or you could just be waiting for the bus.
Right. The pre-activity moment.
Exactly. And you've put on your best gear, your biggest, warmest, most expensive thermal jacket. You are glorious. You are bundled up so tight, and you feel that initial rush, that perfect, impenetrable warmth.
That's the best feeling. It's that peak satisfaction of being prepared. You step outside and you think, I've done it. I have beaten winter.
You have. You've maximized your thermal resistance. You are winning the war against the cold. But then you start moving.
Here it comes.
You pick up that heavy courier bag, or you start shoveling the driveway, or you just have to break into a sprint for 2 blocks to catch the train that's about to leave.
Your internal engine just kicks into high gear. Your metabolic rate spikes.
And for about 5 glorious minutes, you're still fine. You feel great. You're sort of coasting on the inertia of that perfect initial warmth.
But your body, it has other plans. It has to dump all that new heat you're generating. And it only has one real way to do it.
It activates the sweat glands. And that, right there, is when the betrayal starts. It's that insidious dampness, that sticky, clammy feeling that starts on your back, maybe the back of your neck.
And you're still trapped inside your winter armor, that, 13-millimeter thick down jacket.
Ammo.
And it's doing its job perfectly.
A little too perfectly.
It's trapping all that heat and now all that moisture right against your skin.
The irony is just, it's brutal. The very thing you put on to protect yourself from the cold is now the thing that's actively making you miserable.
Yeah.
It's making you clammy, and it's going to make you freeze the second you stop moving.
So that amazing thermal gear, designed to keep heat in, suddenly becomes your biggest liability because it has no idea what your body is doing. It's static.
So the mission statement of this research, when you boil it all down, is actually pretty simple. We need warm clothing that is smart enough to know when we are working hard and need to cool down.
It needs to be intelligent, autonomous,
and responsive. It needs to stop being this fixed barrier and start being a secondary adaptive skin.
And this team, they found a way to do it. And it's all based on one single, simple trigger.
Moisture.
Just sweat.
Okay, so let's unpack the absolutely incredible engineering journey that got them there.
Let's do it.
To really get why this innovation is such a massive deal, we have to start with the human body itself, which is, it's a masterpiece of thermal engineering. Our own built-in mechanisms for staying warm or cool are just unbelievably dynamic.
Right. Think about it for a second. Your body is making these constant, tiny adjustments all day long without you even noticing. When you get cold, your blood vessels constrict, right? It shunts warmth to your core to protect your organs. You start shivering, which is just your muscles contracting to generate heat.
And when you're too warm, it's the opposite. It opens up those blood vessels to get heat to the skin, and it turns on the sweat glands.
It's a high-tech active cooling system. It's got variable fan speeds, liquid cooling, all of it managed completely autonomously by your brain. It's amazing.
Okay, and then you have traditional warm clothing. In response to this incredible high-end biological machine, what is it?
It's a rock.
It's a giant heavy blanket that's stuck on one setting. It is the definition of a static solution for the most dynamic problem your body faces every single day.
Exactly. It doesn't matter if you're standing perfectly still in a 0-degree wind or if you're sprinting up a hill carrying a heavy pack. Your jacket's thermal resistance is fixed. It's the same.
The super heavy down jacket you put on for a gentle, 10-minute walk to the store is the exact same jacket you're wearing when you're out there for an hour, vigorously shoveling snow or loading boxes onto a truck.
The clothing just completely ignores that massive, rapid spike in metabolic heat you're generating. It has no clue.
And this mismatch, as our sources really dig into, it moves pretty quickly past just being uncomfortable into some real health stakes. This isn't just about feeling a bit clammy.
No, it's about actual physiological danger. When your warm clothes trap all that heat during exertion, you run the risk of some really serious health issues. Things you would normally associate with, like a summer heat wave.
Right.
But they're happening inside your winter coat. You can get heat cramps, heat exhaustion, and in serious cases, even neurological disorders. Your body's inability to get rid of that heat quickly puts it under enormous stress.
And then there's the other side of it.
The other side of it is that all that trapped sweat then rapidly cools you down the moment you stop moving, which can risk hypothermia. So you're bouncing between overheating and freezing. It's a vicious cycle.
So who is most at risk for this kind of thermal ping pong? Our sources point squarely at one key demographic.
Outdoor workers.
Yep.
People like couriers, sanitation workers, traffic police, landscapers, folks in high-effort jobs who often have to wear a standardized uniform.
They can't just stop what they're doing, strip down to a thin layer, wait 20 minutes to dry off, and then put all their layers back on. It's not practical.
They're stuck. They're stuck in this static, insulating gear that has to cover this massive thermal range. And a lot of times, that means they have to wear thinner, under-insulating layers in the morning, knowing they'll overheat an hour later if they don't.
So they're choosing. They're either too cold at the start of their shift, or they're way too hot and damp by the middle of it.
Precisely. The challenge is so clear. We need a mechanism that works by itself for this specific dynamic user, which, led researchers to the big engineering hurdle.
Which is, why haven't we solved this already?
Yeah, why haven't previous smart clothes fixed this for winter wear?
We hear about smart fabrics all the time. You see them in ads. Why can't they just use that existing technology?
Well, most of the previous attempts at these self-adapting textiles, they focused on things like changing the fabric's emissivity or its porosity.
Okay, what does that mean in plain English?
It basically means making the surface of the fabric better at radiating heat away or just allowing more air to pass through it.
Ah, so making it more breathable.
Exactly, and that works brilliantly for thin, cooling garments. Making a summer running shirt better at being a summer running shirt.
Got it.
But here's the critical limitation when it comes to warm clothing. A down jacket works by maintaining really high thermal resistance. It does that by trapping a thick, static layer of air. That's what lowers the heat flux.
Okay, heat flux. That's the rate of heat transfer, right?
Yeah.
How fast heat moves through the material.
You got it. So if you just change the surface color of a big puffy jacket, or you poke a few more pores on the outside of a 13-millimeter thick coat, you haven't actually changed the bulk insulation power of the filling itself. The attic full of still air is still there.
So trying to cool down a down jacket by changing its surface. It's like trying to cool down a fully packed thermos by painting the outside a different color.
Perfect analogy.
You've addressed the external layer, but the real problem, the bulk thickness, is still there.
You've nailed it. The only real solution for warm clothing is to dynamically, physically modulate the thickness of the filling material. We need to find a way to make it go from 13 millimeters thick down to 2 millimeters.
But how do you tell a jacket to make that kind of huge structural decision without using batteries or wires or some complicated app?
Right. Some early studies tried using temperature-driven changes, but that fails because the temperature outside might stay at 5 degrees, even while your internal body temperature is going crazy.
The coat needs an internal cue.
Yes. An external temperature sensor has no idea how miserable you are on the inside. So the researchers, they realized they needed a trigger that gives the most direct, the most timely reflection of your body's need to get rid of heat.
The moment that physiological engine starts to ramp up, the moment the sweat glands activate.
The moisture, the rise in humidity in that little microenvironment between your skin and the inner layer of your jacket, that is the perfect instantaneous physiological cue.
So what we need is a jacket that basically smells the first hint of sweat and immediately thinks, okay, emergency protocol, time to slim down.
That's it.
Okay, this is where we shift from the problem to just the pure science of the breakthrough. They couldn't use conventional materials. They needed a filler that was cheap, scalable, and could physically move in response to just water vapor. So what material was the unlikely hero of this quest?
The material they engineered into this new actuator system is natural bacterial cellulose, or BC for short.
Bacterial cellulose. That sounds like something you'd find growing in a jar of kombucha, not something you'd put inside a high-tech winter jacket.
And you wouldn't be totally wrong. BC is actually produced through fermentation by bacteria. It's naturally derived, it's super high purity, it's durable, and it's highly crystalline. From a sustainability angle, that's a massive head start.
Okay, but why BC? Why not use a standard synthetic hygroscopic material? I mean, we've got plenty of nylons and other polymers that absorb moisture.
That is a fantastic and critical question because your standard synthetic hygroscopic materials,
Huh?
yeah, they absorb water, they might swell up and change shape. But crucially, when they swell, they generally become less rigid, they get softer.
And they often get thicker.
Exactly.
Wait, hold on. If the material swells and gets thicker when it gets wet, that is the exact opposite of what we want. We need it to get thinner when it's wet so we can dump heat.
Precisely. And that's the core reason why conventional hygroscopic materials could never solve this warm clothing problem. If you put a simple swelling material inside a jacket, you'd start to sweat, it would swell up, and your insulation would actually get better.
You trap even more heat. Oh, that's a nightmare.
It's a disaster. So the BC solution isn't just about finding a material that likes water. It's about engineering it into a system that performs a completely counterintuitive structural movement. And that, right there, is the heart of the breakthrough.
Okay, so how do they do it?
It all relies on this carefully balanced physics concept called a strain gradient. Let's dig into the unique actuator mechanism they built. They didn't just use BC by itself. They created a bilayer membrane. Think of it like a microcomposite, an engineered structure.
A bilayer. So 2 layers. What were they?
So you have the active layer, that's the BC, which is the moisture sensor. And then bonded to it, you have a rigid passive layer, which acts as the structural backbone.
Okay, and what was the backbone made of?
For that, they used polyethylene terephthalate, heat.
Heat, same stuff used in soda bottles, and ton of other durable textiles. So it's cheap, it's strong, and critically, it's rigid.
Yes. That PT layer is the key to creating the strain gradient they needed. So let's look at the dry state first.
Okay.
State 1, dry conditions. You're at rest, you're not sweating. When the environment inside your coat is dry, so low humidity, the BC active layer naturally releases or desorbs water. It shrinks just a tiny bit.
Oh.
But because this shrinking BC layer is bonded so tightly to the totally rigid and non-shrinking peat layer, that shrinkage creates this enormous internal strain, this pulling force.
Okay, so it's like gluing a rubber band that wants to shrink onto a stiff metal ruler that can't bend.
Exactly. That is the perfect analogy. The shrinking force of the BC, the rubber band, pulls against the unmoving resistance of the PET, the ruler, and that forces the whole composite membrane to curl or bend upwards away from your body.
And that bending is what holds up the entire textile structure, creating those massive internal air gaps, the attic space of still air we were talking about.
Yep. And air gaps equal insulation. So curled up means maximum warmth.
Got it. Okay, now what happens when you start sweating?
State 2, humid conditions. You start working, you start sweating, and the humidity inside your jacket rises rapidly. The BC layer immediately starts to absorb or adsorb that water vapor from the air. As it absorbs that moisture, it swells slightly. And that swelling relaxes the internal strain that was causing it to curl in the first place.
So it effectively pushes back. It flattens the rubber band out against the ruler again.
Precisely. The membrane automatically flattens down towards the body. And when it flattens, the internal air gaps disappear. The attic is gone. And that leads to a dramatic reduction in the overall thickness and a huge increase in heat transfer.
Okay, this is the perfect place for that garage door analogy. Let's really cement this visual, but with the materials this time.
Go for it.
So imagine the inside of your jacket is lined with all these little round 4-centimeter units. The rigid PT layer is like the frame of a garage door. It keeps the whole structure stable and strong.
Okay.
The BC layer is the special sensor lining on the underside of that door. When it's dry and cold, the BC shrinks and it pulls the entire composite door upwards, curling it open. And now you have this massive 13-millimeter tall insulated attic space.
Maximum warmth achieved totally passively.
But the second you start to sweat, that BC layer senses the humidity, it swells up, and it pushes the entire garage door flat against the floor. It completely eliminates that airspace, thinning the coat down to just 2 millimeters. It opens the heat dissipation duct.
No batteries, no wires.
Just the physics of the strain gradient. It's brilliant.
And this leads us to the critical engineering challenges they had to solve during optimization. Because it wasn't enough to just invent the BCPE structure. They had to make it rigid enough and fast enough to actually be useful in a real garment.
Right. Let's talk about that rigidity. Because if the PE layer wasn't rigid enough, the BC shrinking wouldn't cause a nice clean curl. It would just sort of stretch the PET a little bit.
Or buckle. And if the outer layers of the coat are heavy, they could just squash the whole BCPE structure flat, even when it's supposed to be dry and puffy.
Yeah, that would defeat the whole purpose.
Exactly. So they needed to engineer a very specific standing force. The textile needed to maintain a certain level of stiffness to hold itself up against the pressure of the fabric layers around it. They actually calculated the minimum required standing force. It was 0.856 newtons per square meter.
Wow, that's a highly specific measurement of structural integrity.
It is. And after a lot of optimization, they landed on the perfect recipe. The BC layer is 10 micrometers thick, and the PET layer is 30 micrometers thick. This BC10 PT30 composite.
And what did that get them?
That specific combination yielded a standing force of 1.785 newtons per square meter.
Oh, wow. So they more than doubled the minimum required structural force. That ensures that the garage door stays robustly open, even if the jacket gets a little compressed or the fabric is a bit on the heavy side. That's just smart over-engineering.
And beyond just the material ratio, they looked at shape. So the BCPE membranes were these little cellular units. They modeled squares, hexagons, a rhombus shape, and round ones.
And what worked best?
The round membranes, specifically 4 centimeters in diameter, performed the best.
Why the round shape? What was special about that?
The round shape just had a greater bending stiffness. So when the BC shrank, the curved edge of the structure made it naturally more resistant to being compressed. It held a higher residual thickness when it was dry compared to the angular shapes, which tended to crease or fold more easily.
They really optimized everything for structural integrity in that dry, warm state.
They had to. So we've got the material, the structure, the rigidity, the optimal shape. But we also talked about speed. If the reaction isn't quick, the person is already overheating and miserable.
Right, timeliness is everything here.
That humidity signal needs to reach the BC membrane immediately. So to enhance the response time, they did something really simple and smart. They introduced small, round pores, about 5 millimeters in diameter, into the inner lining material of the jacket.
So the pores are like little express lanes for the sweat vapor to get to the BC sensor layers.
Exactly. It's a very simple design choice, but it accelerated the humidity transmission, making sure the membrane responded super fast, typically within about 5 minutes, which is right when that misery cycle usually kicks in.
Okay, and crucially, this whole thing has to be viable for mass production. This can't be some complex lab-only material that costs a fortune.
No, and it isn't. The researchers really emphasize that the BCPE composite can be manufactured using easily scalable processes like blade coating and spraying.
So what does that mean?
It means that replacing the static synthetic fillers we use now with these dynamic BCPP membranes can be done affordably and at a really high volume. This makes it a true commercial contender, not just a science experiment.
That is that beautiful sweet spot, is the confluence of cutting-edge material science and just practical real-world manufacturing. They didn't just solve the physics, they solved the production line.
And finally, durability. You asked about long-term stability earlier.
Yeah, does it wear out?
Well, they put the membrane through 200 cycles of wet and dry conditions, simulating really extreme thermal cycling over and over. And it maintained its shape-shifting property throughout the entire test.
200 cycles is significant.
It is. It was also shown to be stable over a 12-hour period in dry conditions, which means it's not going to spontaneously flatten while you're just sitting still waiting for your bus.
So this jacket isn't going to turn dumb after one harsh winter. They clearly approached this with a real product mindset, not just a research paper mindset.
Absolutely.
So we've established the BC and PET, the strain gradient, the round shape, the fast response. Now we need the hard data, the quantifiable evidence that this actually creates a major thermal advantage. Let's look at the numbers.
The numbers are, and I'm not exaggerating here, they're astonishing, mostly because of the magnitude and the speed of the structural change. So when the humidity inside the test chamber increased from 20%, which is dry and cold, to 95%, which is humid and sweaty, the unit thickness of the material decreased rapidly from 13.2 millimeters down to 2.8 millimeters.
Oh, that's a physical reduction in thickness of almost 80%, and it happens in just 5 minutes. That is a serious transformation.
And that transformation, it fundamentally changes the heat transfer dynamics, which brings us back to that metric we talked about, heat flux. Let's call it Q.
Okay, Q. Remind us again, what is heat flux and why is it the most important number here?
So heat flux is just the rate of thermal energy transfer per unit area. And, normal terms, it just measures how fast heat is moving through the fabric.
Right, so high insulation, like a winter coat, means low heat flux. High cooling power, like a summer shirt, means high heat flux.
You've got it. So when the SAWC fabric was in its thick insulating state at 13 millimeters, the heat flux was measured at 22.23 watts per square meter. That's its low transfer maximum insulation mode.
Okay, and when it flattened down to that 2.8 millimeter state,
The heat flux shot up to 73.78 watts per square meter.
that's more than triple.
More than triple the rate of heat dissipation. In practical terms, that means the fabric suddenly allows more than 3 times the amount of your body heat to escape compared to when it was insulating you.
That magnitude of dynamic change with zero power input is what makes this a revolution. It really is like having a blanket that turns into a fan on command.
And to prove just how versatile it was, the team benchmarked the SAWC against 2 industry standards. They called them traditional textile number 1 and number 2.
Okay, so what were they?
So TT number 1 was just a thin, fixed thickness polyester shirt, about 1.4 millimeters. That's our standard for maximum heat dissipation.
Your basic gym shirt.
Basically, yeah. And then TT number 2 was a high-performance commercial down coat, 13 millimeters thick. That was our static villain representing maximum insulation.
Okay, so how did this smart fabric perform against the best static insulator and the best static heat dissipator?
All right, so in the dry state, when it was supposed to be warm, the SAWC's insulation performance was nearly identical to the commercial down coat.
Really? That close?
Yeah, its normalized heat flux was 0.40 compared to the down coat's 0.35. So the SAWC was only about 14% less insulating than a fixed thickness down coat, which is an amazing and totally acceptable compromise for the incredible versatility it offers.
Okay, so it's almost as good as a regular down coat when it's dry. What about when it's humid?
In the humid state, the SAWC's heat dissipation performance was almost exactly comparable to the thin polyester shirt.
No way.
Seriously. The SAWC's normalized heat flux was 0.69, and the thin shirt was 0.71. It effectively morphs its performance profile to match a thin athletic tee the moment it gets wet.
Hold on, I just need to pause on that for a second.
Yeah.
That is the achievement right there. We are talking about one single piece of material that can functionally replicate the performance of a heavy winter coat and a light summer shirt autonomously.
It completely eliminates the need for delayering.
That's the whole ball game.
And that's the core finding. So when the team calculated the overall dynamic thermal regulation capability, so the total range of heat flux it could cover, they compared the SAWC against that traditional warm coat that's always stuck at 13 millimeters thick.
And the difference was?
The SAWC expands the thermal regulation capability by 82.8%.
82.8%.
That is the metric that defines the massive leap this technology represents. It's not a small improvement. It's not a marginal gain. It is nearly doubling the functional scope of what your clothing can do.
That number, 82.8%, should be carved into the entryway of every single textile engineering lab in the world. And does this still work even when it's like brutally cold outside?
It does. They specifically tested it in severely cold ambient conditions at minus 1.3 degrees Celsius.
Pretty cold.
And even in that environment, which is actively trying to keep the BC material dry, the fabric still successfully increased its thermal regulation capability by 71% relative to the fixed thickness down coat when they applied high internal humidity.
So the structural integrity and the responsiveness, they hold up even when the outside world is aggressively cold.
They do.
That is super reassuring for anyone who lives, outside of a temperate zone. Now, on the practical side, we have to talk about the fact that this material is based on moisture and, well, fabrics get dirty. We mentioned the washing stability, but let's just hit that again because the skeptical listener is wondering if it's going to clog up with sweat and dirt.
It's an excellent point. The researchers specifically tested washing stability over 20 cycles. This was a standard test, just tap water, no detergent, and the thickness change capability remains stable.
So normal wear and tear and standard washing routines aren't going to immediately degrade the BCP8 structure or its responsiveness.
That's what the data suggests. And one final super crucial point about moisture. If this fabric is designed to absorb and react to water vapor, does that mean the whole garment stops breathing? Does it trap all the vapor inside?
That's a great question because if it just traps all the vapor, you're still going to feel clammy, which would negate the whole benefit.
Right. But the key finding here is that the presence of the BCP-EE membrane filling does not notably affect the water vapor transmission or WVT of the overall textile.
So the SAWC, even when it's in its thick, puffy state, it still allows sweat vapor to pass right through the material.
Yes, the garment still breathes. The BC is sensing the concentration of the vapor in that microclimate to trigger the physical flattening, but it doesn't actually block the escape of that vapor from the clothing entirely. This is so crucial for sustained comfort, making sure you don't feel sticky and damp even during that transition phase.
We've gone from a lab curiosity to a proven metric. Now let's get to the true application. How did this technology perform when they actually put it into clothing and tested it on real people moving around in the real world?
This was a brilliant real-world demonstration. They integrated the SAWC filling into some commercial jackets and vests. Then they had volunteers test them under two distinct conditions: low-effort walking, which would be dry conditions, and then high-effort cycling, which would be humid, sweaty conditions.
And they used infrared imaging to actually see the heat escaping, right?
Exactly. They did this really cool thing where they divided the back panel of a vest into different sections. One section had traditional down filling, and the others had the SAWC membranes.
So they had a control group right on the jacket itself.
A perfect control. So when the volunteers were just walking, all the strips were thick and insulating. You could see on the thermal camera they were all holding heat in.
Okay.
But when the volunteers started cycling vigorously, the control strips, the ones with the traditional down, they maintained their static thickness and their temperature profile. Nothing changed.
But the SAWC strips.
They showed an immediate and really notable decrease in their thickness, which correlated directly with a big increase in the normalized heat flux in those infrared images. You could literally see the heat pouring out of those sections.
Wow.
It was the ultimate confirmation of the autonomous regulation. The jacket wasn't responding to the outside temperature, it was responding specifically to the metabolic heat output of the person wearing it.
That is the ultimate proof of concept. The jacket genuinely listened to the difference between a leisurely stroll and a high-effort activity. But, okay, what does this actually mean for the person inside the jacket? They didn't just measure the physics, they modeled human comfort.
They did. They moved from physics to physiology. They used the standard Rayman model to calculate something called the predicted mean vote, or PMV, thermal index.
Yeah.
This index is the industry standard for grading physiological stress levels.
Okay, break that down for us. What does PMV mean to the average person?
Think of it as a scale. It goes from highly uncomfortable cold stress on one end to highly uncomfortable heat stress on the other. The goal for any clothing is to maximize the amount of time you spend in the sweet spot in the middle.
Right.
So the researchers, they defined three crucial zones. First is the no thermal stress zone. That's a PMV between -0.5 and +0.5. That's when you feel perfectly comfortable.
In ideal state.
It's the ideal. And then the overall comfort time is extended a bit to include the zones of slight cold stress and slight heat stress. So from -1.5 all the way up to +1.5.
So they set out to expand the duration of both that perfect comfort zone and the sort of acceptable, I'm not miserable comfort zone.
Yes, and to get a really robust result, they modeled the impact this would have on outdoor workers, specifically sanitation workers, across 20 major cities in China, covering 4 totally different climate regions.
Okay, so what was the quantitative comfort revolution here? What did they find?
The results were, on average, just profound. First, the average total comfort time, so the period where workers were in one of those 3 acceptable thermal zones, was extended by 5.8 hours.
5.8 hours.
That is nearly an entire extra half shift of not feeling miserable on average across all those cities.
That is a massive quality of life improvement for someone.
But the second metric is even more impactful. The no thermal stress zone alone, that period of perfect, ideal, I feel great comfort, was extended by an additional average of 7.5 hours.
Whoa. 7.5 hours, on average, of perfect thermal comfort gained just by changing the filling material of their uniform. That is a complete game changer for someone whose job demands constant physical output in cold weather.
Yeah, and you can look at the specific example they gave for the city of Nanjing. For a sanitation worker on a cold day, the SAWC increased their average comfort duration by 7.1 hours. On particularly demanding days, like one they modeled on February 1st, 2024, the total comfort time was extended by up to 13 hours.
13 hours.
That means the jacket kept them comfortable from the start of their shift to the end of their shift, something traditional static clothing could never, ever do.
And this wasn't just for sanitation workers, right?
Yeah.
They modeled this for other professions too.
Yeah, the benefits held true across the board. They looked at couriers, traffic police, green workers, even electricians and welders. For jobs like traffic police, who might already have gear that provides a decent amount of comfort, the SAWC still notably extended that no thermal stress zone by an average of about 4.7 hours.
So it's not just making the worst situations better, it's making already tolerable situations excellent.
It completely shifts the entire experience from, managing constant physiological stress to just being able to perform your job.
And that leads to a really fascinating and, I think, profound socioeconomic implication that the researchers brought up.
The modeled income potential.
Yes.
Because the SAWC so dramatically extends the period that a worker can comfortably and safely keep performing their task, the sources suggest that this extended comfort time could be converted into increased working hours and productivity.
So the argument is, basically, less time spent taking breaks to warm up or cool down, less fatigue from thermal stress. That equals more productive time on the clock.
That's the theory. The researchers actually modeled this potential income growth, and some of the figures they're startling, with some areas showing theoretical modeled increases of over 600% in potential income growth.
Now, we have to be really careful here. That 600% is a modeled maximum, right? It's assuming that every single hour of added comfort time is instantly converted into higher income and productivity, which isn't always how the real world works.
Absolutely. It's a maximum theoretical cap, a ceiling. But what it does is it emphasizes the sheer magnitude of the social potential here. This textile innovation doesn't just promise warmer winters, it promises a greater capacity for sustained, comfortable work, which has really profound implications for the working poor and for anyone in a high-exertion outdoor profession.
It fundamentally reframes clothing. It's not just protection anymore. It's a tool for enhanced physiological performance and even economic empowerment. I mean, that is the true mic drop of this research.
And the future trajectory for this stuff looks really bright because of that low cost and scalability we mentioned earlier. This isn't just going to be restricted to heavy winter coats. This same BCPE technology can be used in dynamic sportswear, specialized equipment for mountain climbing, any kind of general outdoor gear.
The jacket is really just the beginning.
Of course, continued research is needed. They need to look at extreme weather performance. How does it do in tropical humidity combined with cold or in subarctic conditions? And they need to confirm the long-term durability beyond those initial 20 washing cycles. But the foundation is undeniably set.
So what does this all mean when we put all the pieces together?
I mean, it means we have successfully achieved intelligent, autonomous, sweat-activated thermal regulation. We've replaced this century-old philosophy of static insulation, where the garment was just a barrier fixed in time, with a system where the very structure of the garment physically changes in real time.
And it's listening to the most direct feedback cue your body can possibly provide.
The jacket isn't just protecting you from the cold anymore. It's dynamically partnering with your body's own temperature regulation system. It is truly, finally, adaptive clothing.
And this technological leap, it raises a really fascinating question for the future, something for you to kind of mull over.
And it's a big one. If we can perfect personal, autonomous, adaptive comfort systems like this, if we can make our clothing into a highly efficient secondary skin, what happens to the massive amounts of energy we currently dedicate globally to heating and cooling entire buildings?
Right. If every individual person is perfectly regulated by their own clothing, maybe the need to keep every office, every factory, every school at one fixed narrow temperature range, 247, maybe that drastically diminishes.
Could this textile innovation, by solving personal comfort, actually become a revolutionary global energy conservation strategy? Could it dramatically reduce HVAC demands worldwide? That is the macro impact of this incredible microengineering.
The deep dive into bacterial cellulose just became a deep dive into global infrastructure. A conversation for another day. Thank you for taking this deep dive with us.
Always a pleasure.